Okay, welcome everybody to the second Simon's Rock First Friday Math Seminar. A little bit of a mouthful. So this is our monthly mathematics seminar on the first Friday of every month. And today I'm so happy to have Ethan Ackelsberg. Did I get your name right?
Yeah, that's right.
So, and a former Simon's Rocker. We were just talking earlier how we love to connect with our former students. So Ethan is a PhD candidate at Ohio State University now, and he will be speaking to us about Ramsey theory. So from the pigeonhole principle to ergodic Ramsey theory. So best I get out of the way here and let you take it away. So thank you so much for joining us. We really appreciate it. And the floor is yours.
Okay, thanks. And thank you for inviting me to speak. Let's see, hopefully, I think you need to give me screen sharing abilities.
Ken, I think that you're the meeting host. At least when I joined, it said that it was your room. And so if you go into the security settings, you can enable screen sharing for Ethan.
Oh, I think you just did. Okay, can everyone see my screen now? Great, so I'm doing some hybrid between slides and acting like I'm on a chalkboard, and we'll see how it goes. Please feel free to interrupt me at any point if you have questions. There are a lot of different things that I could talk about more in depth, and so I'm happy to talk more about things that seem interesting or whatever based on participation. Okay, so my hope is that everyone knows what the pigeonhole principle is. Even if you don't, I'll go over it so that's okay. And my other hope is that the phrase ergodic Ramsey theory is fairly meaningless to you right now. And that I will make it at least somewhat meaningful by the end. And I'm excited to hopefully introduce you to this area. Or if you've seen it before, maybe this will be something still interesting. Okay, so I'm gonna start just going over the pigeonhole principle and slowly build up to maybe more and more complicated versions of the pigeonhole principle as a door into Ramsey theory, and ideas from dynamics, combinatorics, and number theory will all come into play as I go along. So let's start just with the pigeonhole principle. So the pigeonhole principle in the usual formulation is if you have some number of pigeons and a smaller number of holes, and you want to put the pigeons into holes, there's one hole that will have at least 2 pigeons in it. And I'm going to write this in a slightly unusual way that will hopefully make sense by the time I've written more statements like it. So what I'm going to say is that for any R, this would be the number of holes. There exists some number n depending on R. Such that if n is at least capital N, and I assign these n pigeons into R holes, then there exists some hole with at least 2 pigeons. Okay, and really the way I want to think about this is I'm taking some set and coloring it with R colors. Each of the color classes is called C sub 1 up to C sub R. And this is saying that I have some set with at least 2 elements that's monochromatic. And this is sort of the phrasing that I'll use from now on, is that I'm coloring my sets and then looking for some monochromatic structure. And in this case, it's fairly easy to get what capital N should be. We just need n of R to be R plus 1. If we're coloring more than r things with r colors, there have to be two things that get assigned the same color. Okay, and this fairly simple statement, which is little more than basically just stating the definition of what it means for one set to be bigger than another set, has some interesting applications already. There's maybe some people have heard the claim before that there are at least two people in New York City with the exact same number of hairs on their head. You can get that from the pigeonhole principle and some basic known things about the approximate number of hairs that people have. But I'm not going to talk so much about that. I'm going to talk about some applications already that we can get to number theory just from this simple statement. So let me just state Dirichlet's approximation. So this says it's going to be a theorem about approximating real numbers. So I take some real number alpha, then for any natural number n, I can find integers p and q where q is at most n, such that alpha is approximated pretty well by the rational number p over q. And what I want here is an approximation of this kind. And since q is at most n, I can replace q times n with 1 over q squared. Okay, so this is some fact about how well you can approximate numbers by rational numbers. And this just boils down to the pigeonhole principle. So I will give this proof in maybe some detail. I think as I go on, any proofs I give will be less and less detailed. But the first one should have some amount of information. Okay, so what's the idea? I'm going to consider this sequence. So instead of looking at p over q, I can look at trying to get q times alpha to be close to an integer. So I'll look at the sequence alpha to alpha up to n alpha, and I'm going to take this mod 1, meaning whatever my number is, I ignore the integer part and just take all the stuff after the decimal point. So I get a number between 0 and 1. And if I want alpha to be close to p over q, right, I just need q alpha to be close to either 0 or 1 when I go to the 0, 1 interval. And so I can look at the interval from 0 to 1. That's not a very good line. And I can break this up into, say, n subintervals. So this is 1 over n, 2 over n, and so on. And then I get n minus 1 over n. And the first thing to notice is if I have some q alpha that's in the interval from 0 to 1 over n, then we're done. Because that's within 1 over n of one of the inputs. So let's suppose that's not the case. Well, now we only have n minus 1 intervals, but these points, alpha up to n alpha, there are n of them, and so there has to be some interval with at least 2 points. So by the pigeonhole principle, there exists, say, q1 less than q2, such that q1 alpha and q2 alpha are in the same interval out of these remaining n minus 1. And so if we take their difference, Well, the interval has width 1 over n, and it's half open, half closed, so they have to be within 1 over n of each other. So we're really not using anything but the pigeonhole principle here. And we get some results about approximating any number whatsoever by rational numbers. Okay, so I think there are a lot of questions that we can ask after seeing this result, and I'll maybe touch on some of them as I go along and see where using ideas from dynamics can give us even stronger claims about what happens when we multiply alpha by some integers. So if we look at what we just proved, we showed, well, alpha can be approximated well by rational numbers, or the way we actually proved this was to look at integer multiples of alpha, and we showed that we can always make that as close as we want to an integer. And then if we keep multiplying by more integers, we can get that this sequence of integer multiples of alpha is dense mod 1. So this just follows from the proof we had, but there are plenty of questions you could ask, like, well, what if we want something better than density? Maybe it's not clear what better than density would mean, but for example, what if we wanted something like this? So density just means we get arbitrarily close to any point we want, but it doesn't tell us about how those points get distributed in space, how much time we spend, the left half of the interval versus the right half of the interval, or anywhere else. But using some different tools, maybe we could prove something like this for continuous functions f. So this would give us something stronger than density, that not only are we getting points well, but we actually can estimate the integral of a continuous function by just sampling along our path. And there's nothing really dynamical yet. I haven't even really talked about what I would mean by what a dynamical system is, but one way of thinking about this is we can think about this thing as some kind of time average. So we can think about, we're going along our sequence just in order. We have alpha, then 2 alpha, then 3 alpha, and we're measuring where that is in the interval, and then averaging as we go along in time. And this right-hand side, I'm going to think of as a space average. And depending on sort of where we go, we may see how dynamics can help with showing some relationship between time averages and space averages to say more refined, give us more refined information about a number theoretic result like this. Okay, and we could also ask things about more general sequences than just n alpha. Like maybe we'd want to know something about what happens to a sequence like n squared alpha, or I don't know, just maybe some polynomial times alpha. Or if you like number theory, you like dealing with the prime numbers a lot. And so maybe you want to know what happens if you go along prime multiples of alpha. Or you could ask about much more general sequences, like maybe log of n, or we could look at powers where we're no longer looking along an integer. And in all of these cases, you maybe need some different tools, but various other ideas from other areas of mathematics can answer these questions. And so I won't get to answer all of them today. It turns out that for polynomials or for prime multiples, we get density and the stronger property I've written here for n alpha called uniform distribution. And for log n, we still get density, but we don't get uniform distribution. And so there's some distinction between these phenomena that depends on behaviors of these sequences. Okay, but this is sort of an aside of just what kinds of questions we can ask after proving some results. And these further questions maybe require ideas that are going to be much more complicated. The pigeonhole principle, but the pigeonhole principle gets us somewhere. Yep, Bill.
In those last two, the alpha went away. Are
Yes.
you multiplying? Are you looking at a different sequence that doesn't have anything to do with alpha anymore?
You could multiply by alpha if you want. There's no so the first two cases I want to multiply by alpha because if I'm just looking at integers mod 1, nothing interesting is happening. Whereas once I start taking non-integer powers or I'm taking a log,
Okay.
I'm already getting fractional parts. And so the alpha wouldn't really do much for me. That's all. You could add the alpha and it would have the same behavior. Yep. Answering that question.
Is log n some kind of cutoff point, or if you went to like very slow algebraic functions, would it still be a problem? Like if you did.
So log n, you want things that grow faster than log n to get if you want uniform distribution. So for
Right,
density, so for density, if you have something that's growing very slowly, you're likely to get density because things get really close together. But it's going to spend too much time in, right? So log n is growing fairly slowly. So if you start looking at differences, they get very small and you're spending large portions of time in the same space before you get onto a farther interval. And so you're not going to get uniform distribution. But if you change your averaging scheme, so you can still take some kind of time average, but you won't want to, you'll want to give different weights to different points. You can still get, so it's well enough behaved that you can still estimate integrals if you average differently. And that's going to be true for most well-behaved functions. Like if you have something that's increasing with maybe some reasonably well-behaved derivative, you should be able to come up with some kind of averaging scheme that will work, but it may depend on the growth rate. Okay, so let me get back to just thinking about the pigeonhole principle and seeing how some slight improvements to the pigeonhole principle can already get us some fancier results. So the pigeonhole principle in the first version was about wanting to get at least 2 points of the same color, or 2 pigeons in the same hole. But what if we wanted sets with 3 elements or 4 elements or something else? Well, we can definitely do that. And so I'm just going to state this version here. So now we're going to look at, again, some number of colors. And we have some number that's going to be the size of a set that we want to be monochromatic. Well, now there's still going to exist some number now depending on R and K. Such that if N is bigger than capital N, and again, I do some R coloring. Then I'll be able to find a monochromatic set with at least K points. Okay, and this is maybe unnecessarily fancy as a statement again. We just need N to be equal to what? R times K minus 1 plus 1. Right, so if you want to avoid having K points in any color, the best you could do is have each color have K minus 1 points. And as soon as you have one more, you're going to have to get a set with K elements that's monochromatic. Okay, and so this is a slight improvement on the first version of the pigeonhole principle we saw. And it leads us to, with some extra steps, a non-trivial result in graph theory, which I'm going to state sort of colloquially so I don't have to define graphs. And any term that's unclear, I'm just going to leave unclear, and hopefully the proof will make it more clear. So what is this statement? So in any group of 6 people, there are either at least 3 who are mutually friends, or at least 3 who are mutually strangers. Okay, and this is in a world where everyone is either a friend or a stranger. So if you want to replace friends with acquaintances to make it more realistic, feel free. This is just how it's usually stated. Okay, and so what's the proof? Well, let's look at one person. So there's one person, there are then 5 other people. And I'm going to draw, say, a blue line to any person that I'm friends with and a red line if they're a stranger. Well, by this version of the pigeonhole principle, we have 5 different people that we have some relationship with, either friends or strangers. And there are only 2 things that they can be. So, well, R is 2, and if we do 2 times 3 minus 1 plus 1, that's 5. So there has to be, in one color, 3 people. And we'll just say that we're friendly and have at least 3 people who we're friends with. And now we can just look at any of the edges here. So if I look at these 2 people, they're either friends or strangers. If they're friends, then that's going to form a triangle that's in blue, and we'd have 3 people who are mutually friends. And this is true of all of those edges. So the only way to avoid having mutual friends there is if all of these edges here are red, and now we have a red triangle where 3 people are all mutually strangers. Okay, and so that finishes our proof. So this is the first non-trivial case of Ramsey's theorem. If you wanted to have groups of 4 instead of 3, I think you have to get to 18 people. I might be misstating that. And for any collection, any size that you want, there's some large enough group of people where you'll be able to find that number that are all mutually friends or all mutually strangers. But computing that number is incredibly hard, and I don't think there will ever be a general formula that people know. Okay. So already with just these simple statements of the pigeonhole principle, we're seeing at least pieces of non-trivial results in number theory and in combinatorics. So let's try to get something non-trivial in analysis. So the last 2 have been all about finite sets, but we can do infinite sets and maybe state things in an even simpler way. So let me just write it this way. If I take some finite coloring of the natural numbers, then I can find an infinite set that's monochromatic. Okay. So nothing surprising here. I can't take an infinite set, break it into finitely many pieces, and somehow have all of those finite pieces be finite. But applying this already produces a nice result in analysis, which is the Bolzano-Weierstrass theorem. And I'll say it this way. So let's say every bounded sequence in the real numbers has a convergent subsequence. Okay, and I'll give a very brief sketch of the proof here. So let's say our sequence is bounded between A and B. I'm only going to actually care about the case where I have two colors. So let's split this interval in half. And I've taken some infinite set, my sequence, and split it into two pieces. I look at the points that are in the left half of the interval and the points in the right half of the interval. One of those has to have infinitely many points. So let's say there are infinitely many in the left half. Then I can split that in half. And one of these two pieces has to have infinitely many points again. And we just keep doing this. So maybe it's here, then here, whatever it is. We keep breaking it in half. We have an infinite set somewhere. And we get narrower and narrower intervals as we go along. So whatever happens in this process will eventually get down to a single point. And we can construct from this a subsequence of our original sequence converging to that point. And that's all the detail I'm going to give here. So we can see the Bolzano-Weierstrass theorem as, at least in this approach, applying the pigeonhole principle infinitely many times. And I think I'll get to it later of showing how Ramsey's theorem, which we saw the first case of maybe on the last slide, can be used to do these infinitely many applications of the pigeonhole principle all at once and prove the Bolzano-Weierstrass theorem in just one step instead of infinitely many. Okay. But I think already this has provided a variety of results in different areas, all coming from some idea related to the pigeonhole principle of, just looking for, we take some large set, if we break it into finitely many pieces, there's one piece that's still large. Okay, are there any questions before I get to a slightly different pigeonhole principle that might require some more thought? Okay, so this next one I'm calling, so temporarily, for the purpose of this talk, a continuous pigeonhole principle. So instead of thinking about taking pigeons and we just assign them to this these finitely many possible options for holes, maybe you want to think about you have some objects with some size, and if the sum of all the sizes of the objects exceeds the amount of space that you're putting them into, you're going to have overlap. So at least this is the same idea as the pigeonhole principle, even if it's a little bit different. And so let me write this in some formal way. So the thing that's going to be playing the role of the number of colors from before is now just going to be some number. Then there's an n depending on r, such that if n is bigger than n, and so now what do I want? I want some collection of objects whose total size, or the sum of their sizes, exceeds r. So now I'm going to look at some sets. Let's see. So sets in a space with total measure r, and the sum of their measures is at least n. Then I can find two sets that have some overlap. And I'll say what I mean by measure more formally. But again, you can think about this as you have a bunch of objects with some volume, and you're trying to shove them into a space of smaller volume. This is going to require having some overlap. And so here, again, this calculation of n is easy. It's just going to be that n is equal to r. And so let me say what this word measure means. So you should think about this measure as some abstract notion of length or area or volume. And at least if you're, I think, I don't want to, get too technical. At least if you're thinking about lengths or areas or volumes, I think that will be sufficient. But just to write it down, X is going to be some set, and then mu is our measure, which is going to be a function assigning non-negative values to subsets of X. And you have to be careful. This is where the technical part comes in, is you have to be careful about which subsets you can measure. I don't want to worry about that. Okay, what this should do, if I take the empty set should not have any size to it. That will have measure 0. And if I have some collection of disjoint sets, and I take their union, I should get this sum. So here, I want I to be a countable set, and this collection should be pairwise disjoint. So for instance, if I want some way of measuring sets of real numbers, I could assign to each interval the length of the interval. So AB would have length B minus A. And then if I have a bunch of disjoint intervals, I want the total measure to be the sums of their lengths. And for more complicated sets, it's maybe not totally clear how you would compute the measure, but at least there's some consistent way that you could assign a length to basically any set you would deal with of real numbers. Okay, and so the reason I want to talk about measures at least somewhat is because this is what I study for doing dynamics. And this version of the pigeonhole principle is essentially equivalent to one of the most basic results in dynamical systems. But again, it's a sort of basic pigeonhole principle type results that can lead to all sorts of interesting applications, especially if you upgrade it in certain ways. So let me talk about what a dynamical system will mean for me. So very abstractly, by a dynamical system, I'm going to mean some set with some kind of structure and some map from the set to itself that preserves that structure. So these are people who know what these words mean. I could consider a compact metric space and some continuous map on that space. I could look at a diffeomorphism on a smooth manifold. These are both interesting things that people study. The thing that I'm most interested in is taking a probability space. So this is a measure space like I talked about on the last slide, where the total measure is equal to 1. And the structure preserving transformation is going to be a measure preserving transformation which means, so if my transformation is T, the measure of the set of points that end up in a set A is the same as the measure of A. Okay, and so I'll write down a few examples that you can maybe think of for what a measure preserving system would be, and there are many more that you could come up with. So some examples might be, we could take X to be the 0, 1 interval, and a transformation might be taking X plus alpha mod 1. And so this is the dynamical system we might care about for sequences, like for understanding the behavior of a sequence and alpha mod 1. Or if you would like dealing with binary expansions of numbers, we could take a transformation where we multiply a number by 2 and take the result mod 1. And studying this dynamical system would tell you probably anything you want to know about binary expansions of numbers. Okay, another system to maybe consider is infinite sequences of zeros and ones, or maybe you want to think about these as infinite sequences of heads and tails. And our transformation is just going to be a shift by 1. Okay, and I didn't actually explicitly say what the measures are. So in the first two cases, so in the first case, if you want this to be measure preserving, your measure is going to have to be the one that assigns to every interval the length of the interval in our usual sense. In these last two, there are all kinds of measures you could put on these spaces, but a natural one to put would be, well, in the second case, you still just consider lengths of intervals as usual. And for 0, 1 sequences, we could take a measure that treats each coordinate as an independent variable with, so we have some probability of 1/2 of getting a 0 and 1/2 of getting 1. And this system would then be modeling, say, infinitely many flips of a fair coin. Now, maybe it's worth mentioning the last two systems I wrote down here are actually the same system. So understanding random coin flips and understanding binary expansions of numbers are actually the same thing. But these are different ways of thinking about it. Okay, so why do I want to talk about measure preserving transformations? Well, we can talk about now a sort of dynamical version of the pigeonhole principle, Poincare principle. So this says that if we have some measure preserving system, which I'll abbreviate by MPS, and I'm going to take A with positive measure. The claim is that I can then find some time n such that A intersects the nth iterate of itself. Okay, so maybe before I prove this, let me tell you why Poincare cared about this problem and what this theorem at least meant to him. So Poincare was interested in proving that the solar system is stable. So if you think about the solar system, you have the sun, all the planets, moons, all these other objects. if you want to understand the orbits of planets in such a complicated system, you're probably not going to be able to write down exactly what the trajectory of all these different objects is going to be. So as soon as you introduce, more than just a sun and a single planet, describing orbits exactly is an incredibly difficult problem. But maybe we can still say something qualitative about the behavior of the solar system over long periods of time. So what Poincaré wanted to say was that, well, okay, we can't describe these orbits exactly, but it seems like there's some kind of periodic behavior to the solar system, or maybe at least almost periodic behavior. Let me close it. So one way of interpreting this is we could take as our dynamical system all of the different objects in the solar system with maybe their position and velocity. And our transformation just tells you all of their positions and velocities after, 1 minute. And so if you apply this transformation, that just puts you forward 1 minute in time. What this theorem then says is that whatever the current positions and velocities of the solar system are, after some period of time, will come arbitrarily close to those current positions and velocities. So the set A you'd want to take would be some neighborhood of those positions and velocities, and this would imply that. So this, again, I'm going to show you the proof. It's basically just the pigeonhole principle, but it tells you something deep about long-term behavior of something as complicated as the solar system, and I'll also show you hopefully some combinatorial consequences. Okay, so the proof is we just take these sets. So we have A, free image of A, okay, so we just take A and all of its iterates. Well, this system is measure preserving. So I'll just say mu is equal to mu of A for all of these sets. So if we take enough of them, the sum of their measures is eventually going to be more than 1, and so we'll have to have some overlap. So our pigeonhole principle implies that there are, let me just do, say, I less than j. Such that these two things intersect. And, well, now we can use that it's measure preserving and cancel a factor of t to the I. And that's Rn. Okay. So this was our first taste of a dynamical result. How can we use this to get more things in combinatorics or number theory or these other places? Let me at least show you one application. This is not how this lemma was originally proved, but I'm going to introduce dynamics to give a much simpler proof than what Hilbert came up with. So Hilbert was trying to prove something about irreducible polynomials of two variables. I don't actually know exactly what the result was, but along the way, he needed this lemma that if we finitely color the natural numbers, then there are arbitrarily large monochromatic K cubes. So what do I mean by this? I mean that for any K, I can find numbers x0 up to xk such that this configuration maybe I'll use J to not confuse things, is in one color class. Okay, and so why am I thinking about this as a cube? Well, if instead of x0 up to xk being natural numbers, if they were vectors, and I tried drawing a picture of this, I'd start getting cubes. So if this is our point x0, and I drew say, x1 in this direction, and x2 in this direction, then I'm going to start, so here I get a square. If I added an x3 and think of that as another direction, I'll get a cube, and I keep getting higher dimensional hypercubes. Okay, now this is a little misleading, right? They're all lying on the same line. They're all natural numbers, but we can think about it as some sort of geometric object if we want. Okay, so how does one prove this thing? Well, Hilbert had some complicated combinatorial proof, and to be honest, I don't know what he did, but it takes some work to do it. The way I know how to do this is to do something a little bit strange. So I'm going to tell you actually basically which color class this has to happen. So what I want to do is introduce some dynamics to this problem and apply Poincaré's recurrence theorem over and over again to get this result. So let's define, say, upper density of a set. So if I have some set E, the upper density is just going to be the portion of the natural numbers occupied by E. So I'll take a limit, and just to make sure things exist, I'll take a lim sup. Of this quantity. So I count how much of the interval 1 up to n is occupied by E, divide by n, and then take a limit. And the claim is that, well, okay, so maybe at least one CI has to have positive upper density. If we break it into finitely many pieces, there has to be one piece that it occupies some positive proportion of the natural numbers. And then the next thing to do is basically pretend that we have a dynamical system. So this is not actually a probability space that I'm going to write down, but we can treat it like one and use tools from dynamics. So I'm going to take the natural numbers. I'm going to treat this natural density, it's some reasonable notion of size, and I'm going to treat it like it's a probability measure. And now my transformation is that I just add 1 to every number. I'm going to pretend that this is a measure preserving system. And if I start applying Poincaré's recurrence theorem, well, what does this say? So then there's going to be an x1 such that the density of E intersected with E minus x1 is positive. And then I can apply it again. There exists x2 such that, well, I take this as my new set, E intersected with E minus x1. And now I intersect that whole set with itself shifted by x2. And that's positive. And you just keep going. Now, if I take a point x0 in this big intersection here, then unraveling this is going to mean, well, x0 is an E, x0 plus x1 is an E, x0 plus x2 is an E, x0 plus x1 plus x2 is an E. And so I get these cube configurations in my set E. And that's the end of the proof. Okay, and so I want to highlight a few things here. So one, we started with a results about partitions. So the result says if I take the natural numbers, I break it into finitely many pieces, one of those pieces has to have large hypercube configurations. The way to prove this was actually to come up with some notion of largeness that automatically gives you hypercube configurations. So instead of thinking about a partition result, I said, as long as my set has positive upper density, then I get hypercube configurations. And then, well, anytime I take a finite partition, one of the pieces has to have that property. And so we have this notion of largeness. The second thing is that by introducing some dynamics, we actually made this result. We opened up sort of new tools available to us that make this a rather short proof. That if you don't use some idea like Poincare recurrence theorem, this is a much harder result to prove. And the last thing is that with this approach, we actually get something a little bit better than the initial result. So the initial result was just that we have some k cube. But in the end, these x zeros are coming from some set with positive density. So we actually get an abundance of k cubes. We have some cube configuration where a lot of different shifts of this cube are still in this one color class. And so these are sort of general themes that occur in Ramsey theory, so Ramsey theory is about these sort of partition results. And these general themes all appear, and it turns out that introducing dynamics and modeling things as dynamical systems is an incredibly useful tool for proving these kinds of results. Especially if the relevant notion of largeness is some kind of density that we can think of like a probability measure. And so, yeah, so maybe I'll end here since it's just about 5. And if there are questions about things, I can tell you some other results that are much more far-reaching than this. But I think this example already gives you a sense of where understanding something dynamically is a useful tool. And of course, if you have stronger dynamical results than something that's basically just the pigeonhole principle, you're going to be able to prove much deeper combinatorial results that are maybe more interesting.
So let us thank our speaker with a round of applause or some reactions. Some Simon's Rock snaps. Are there any questions for Ethan?
I have like a really minor question that I just must have spaced out and not asked, but it really doesn't matter for anything, I guess. So back when you were talking about these like transformations, why was it always T inverse?
Okay, so yeah, this is a technical thing that I didn't really want to talk too much about. The reason is that if you have a measurable map, so if I take forward images, I have no guarantee that the resulting set is actually going to be measurable. That's one reason. And the other is that so what I'm really interested, the dynamical system is really applying, here, I have some extra space here. So what we're actually interested in is maybe points, and points we take tx, t squared x, and so on. Right, so in order of a point, we are going to apply t to it and take forward images. If we're looking at sort of set dynamics, well, what would it mean for tx to be in A? That would be like looking for x to be in the pre-image of A. So if you want to understand something about the forward orbit of points, you want to study instead the backward orbit of sets, or the orbit under the pre-image. So it's part of it is a measurability concern, part of it is this difference between thinking about sets and thinking about points.
Cool, thanks.
I've got a question about these measure preserving transformations. Do they have any regularity properties? Like, are they almost bijections or?
So, okay, so you can always embed a measure preserving system into an invertible system, but they can be very far from being bijections. So let's see, so like, right, this system here, if I multiply by 2, that map is going to be 2 to 1 everywhere. So I could draw this, I could even draw a picture here that is maybe helpful. So my map is doing something like this. If I draw any sort of piecewise linear functions I want here, I can have a bunch of other pieces. So it can be very far from being a bijection. But as I said, this system multiplying by 2 is the same as this shift here. And if I took by infinite sequences instead, so I have not just indexed by the natural numbers, but by the integers, I could shift both ways and I get something invertible. And whatever measure preserving system you start with, you can always do something like this where you embed the dynamics in something that's invertible. But there are many reasons to care about non-invertible systems, especially if you want to study like expansions from and get some information about binary expansions, continuous fraction expansions, anything like that.
Do you work on metric measure spaces?
So one thing to notice about this sort of last result I showed you is that I was using the Poincare recurrence theorem, which is something that applies to any measure preserving system whatsoever. And one of the things that happens is if you want combinatorial results, you basically have to study completely abstract measure preserving systems. So the answer is no. And it's because with the kinds of results that I'm interested in proving, I need to prove it about completely abstract spaces. Now, in the process, you start introducing various tools that reduce the problem to specific classes, but there are definitely people who work on specific kinds of spaces. That's not what I do.
So the extra structure doesn't really give you any extra mileage, at least in the arena you're thinking about.
Right. If you start imposing extra structure, you're going to get weaker combinatorial consequences.
Do we have other questions for the speaker?
Yeah, just one quick. So when we were pretending that this thing was a measure preserving space, how far diluted were we and how much work would we have to do to get the result that we got?
Okay, so in one sense, so it is true that if you start shifting sets and taking their densities, the density is preserved. The thing that's not true is that density is a measure. It's very far from being a measure. It's not even finitely additive, for instance. So the actual, and I didn't want to get into this sort of technicality, you can prove that anytime you have some set E, say here, with positive measure, then there exists a measure preserving system and some set A with the same measure of E such that something happens. So what do I want? The density okay, so because the natural numbers are not actually a probability space, and there's no way you're going to introduce a probability measure because it's a countable set, or at least an interesting probability measure. You can't really say anything about point dynamics. But if you are interested in a specific set with positive density, you can find a measure preserving system that models the set dynamics of E up to some inequality that has to do with the fact that we have this lim sup and it's not just a limit. And so if you want to prove, right, all we really cared about was the positivity of some intersection. So if you can prove positivity of intersections for measures, that gives you some intersections here. And to prove something like this, you model your set as a 0-1 sequence, where 1 means your number is in your set, 0 means it's not, and then try to look at orbits of your particular sequence, get some space there, and construct a measure there. It's a involved technical argument, but not too difficult to prove.
Okay, that answers my question.
Right, so let's thank our speaker one more time. Thank you, Ethan. We really appreciate it. Our next First Friday Math Seminar will occur on Friday, December 4th. You are all very much welcome and encouraged to attend. If you want to sign up for our email list to get announcements about that, you can send an email to Bob Putz, that's rputz@simonsrock.edu. Put his email in the chat, and we'll send you announcements for the next First Friday Math Seminar on December 4th. So once again, thank you, Ethan, for your talk. We greatly appreciate it, and we'll see you all next month.